So in this presentation here, I will talk about the methods that are behind our NMR end-to-end software tool HQSpectrum, which is for spectral analysis of NMR. And here's a screenshot of how this looks. So this is a browser-based tool that you can use to assign NMR spectra. And currently it is focused on small molecules in liquid state NMR, but we will also extend the capabilities ever further to more use cases. But now I want to talk about how we do this and what are the kind of methods that we use. And the idea behind it is that you start from the point that you have already an idea of what molecule you have, and then you want to know what is the spectrum of this at a certain magnetic field strength, and then you want to compare this to what you have measured. And to do this, we use simulation. And our simulation has like two steps. First, we say, okay, you put in the molecule, which can be put in 2D or a smile string, and we go to get the NMR parameters. The NMR parameters are the chemical shifts and the spin-spin couplings, often also called J couplings. And then I write this down here also as a Hamiltonian, because the next step is to go and simulate the time evolution of an initial state under the Hamiltonian, which gives you then, if you Fourier transform this, the spectrum. And let's start with the first step, how to get from the molecule to the NMR parameters. To do this, we have implemented the workflow that is shown here, where you start with a structure, for example, in 2D by drawing it, and then you want to first generate a fast 3D structure as a starting point. And then comes a key point that I think everybody who has done quantum chemistry or this kind of ab initio simulations knows very well, also in MD. You have to do conformer sampling. So that's quite critical, that you sample over all possible conformers, since normally also the experiments take longer than the time your molecule needs to average out over all these possible states or all these possible forms. And then you do some additional structure refinement, and then at the end you calculate from this the NMR parameters using density functional theory. And here I show you an example where what we see is kind of going downwards in the darker gray are results of an experiment, and compared to orange, and these are our averaged kind of results where I already calculate the spectrum. And you can also see in gray, in light gray, a case where we really take only one structure, and of course that gives pretty wrong results. So this sampling is very important, and what you will also see, our tool HQSpectrum also allows you very smoothly, and also does this automatically, to shift around the chemical shifts a little bit, such that the remaining difference can be removed just by shifting the spectrum a little bit around. Now, you see here already the spectrum. This we get also then from taking this NMR parameters, writing it down in a Hamiltonian, and then calculating the spectrum from this. And as you might know, that this can be a very hard problem, because in principle, if you really try to calculate the spectral function by really taking the Hamiltonian for all spins, then this scales really, really badly. And the way we solve this, I want to show here a little bit at this molecule, fridolin, which has 50 spins. So 50 spins is definitely far beyond any capability for a numerically exact solution. We also do this at 80 megahertz, so this would be done for a so-called low field device. The sampling over all the conformers is very much possible here in this case, so we have good parameters, but now we need to get parameters to the spectrum, and the way we do this is by introducing clusters, so-called spin clusters. So we use a clusterization method, and the theory behind this is that, okay, one proton on one side of the molecule does not need to know what the spin in the other proton far away is doing. And so you can basically take a certain radius in which you include all the hydrogens, and the rest you can forget, and then you go through your molecule and calculate all these different clusters. And this we have implemented in a very efficient way. And here we, for example, see Fridolin, and what you see is that calculating this for a cluster of size 7, mind you, this is again for 80 megahertz. So, and a cluster size of 7 has basically already converged. You see hardly any difference between going from a cluster size of 7 to a cluster size of 14. And with this, I'm at the end of this presentation. So here I discussed a couple of methods that we use. And if you want to test it out, you can use our free trial. Not all the features are yet in the free trial. For example, you cannot yet draw molecules. And this feature to shift around the chemical shifts is also not yet in the free trial. But nonetheless, I think you will enjoy to test this out, and I hope you will like it. Thanks.